Okay, I think I will.
We can start now.
Yeah, okay, thank you. Hello, everyone, and welcome to the first joint EuroDoc and ChemCatChem virtual symposium highlighting young researchers in the field of organic chemistry and catalysis. So my name is Anne Nijs. I'm the editor-in-chief of the European Journal of Organic Chemistry, and with me today are Charlotte Gerst-Panther. She's the editor-in-chief of ChemCatChem, and we have Judy Chen. She is associate editor of both journals and also Angewandte Chemie. We're excited to host this event today and also to guide you through the program. We have a fantastic lineup of speakers and 3 lectures or scientific lectures plus an interactive Meet the Editor session at the end. President will be Fengxi from the Jiangsu Normal University. She's a current advisory board member of EuroDoc. Then we have Peng Wang. He's our invited speaker from the Shanghai Institute of Organic Chemistry. And lastly, we have Feng Ryan Wang from the University College in London, and he's a current board member of ChemCatChem. Each talk will be about 25 minutes long, and then we have a short question and answer session afterwards. For this, please send in your questions through the chat. After this scientific part, we have then the roundtable discussion with the editors, and here you can ask us any questions related to publishing, the peer review process, and so on. And now we would like to start with the scientific part, and I will hand over to Judy for her welcome words and also to introduce the first speaker. Judy, the stage is yours.
Thank you, Anna, for your kind introduction. Hello, everyone. My name is Qingqing Chen. I'm currently based in Shanghai. It is my great honor here today to introduce you our first speaker, Professor Feng Shi. She's currently EuroDoc's young board member. Feng received her master's degree from Jiangsu Normal University in 2004 and then worked at the same university as a lecturer. She became an associate editor in 2010 at Jiangsu Normal University and got her PhD degree in 2013 at Suzhou University under the supervision of Professor Shu Jiangtu and Professor Liu Zhugong. During her PhD studies, she spent half a year to work as a visiting scholar in the group of Professor Taipeng Long at Nanyang Technological University. She started her independent career from 2013 and was appointed to a full professor at Jiangsu Normal University in 2015. She has a rich publication history on high-impact international journals such as JACS and Angewandte Chemie. She has received many awards and honors, such as Chemistry Journal Award, the 11th Asian Core Program Lectureship Award, National Science Award of Jiangsu Province, Natural Science Award of Chinese Ministry of Education, and etc. Apart from research and supervision, Feng also serves as editorial board members and international advisory board members for prestigious journals, such as Chinese Journal of Organic Chemistry and EuroDoc. Without further ado, I'd like to hand over to Professor Shi. Today, she's going to share us with some recent work achieved in her group focusing on chiral endochemistry. Professor Shi, thank you very much for being here. Then the floor is yours.
Okay, thanks a lot for Qingqing's kind introduction. Can you see my slide?
Yes.
Well?
Yes.
It's working great.
Okay. Thanks so much for Qingqing's kind introduction. It's my great honor to join this event and give this lecture on behalf of EJLC. Today, my topic is chiral endochemistry. As shown here, chiral endo derivatives are widely found in natural products, pharmaceuticals, chiral catalysts, or ligands. So the catalytic asymmetric synthesis of chiral endo derivatives has absorbed great attention from the synthetic community. The chiral endochemistry started from 1999. In that year, Johansen established the first catalytic asymmetric synthesis of chiral endo derivatives, while the reaction of endos with imines on the catalysis of copper with the chiral ligand. In spite of this pioneering work, the reactive site of endo was limited to the carbon-3 position, and the reactivity of Indo was confined to nucleophilicity, which resulted to construct new kinds of chiral-Indo-based scaffolds. So there are some changes in chiral-Endochemistry. The traditional catalytic asymmetric transformations of Indos mainly include the following 4 methods. The first is catalytic asymmetric Friedel-Crafts alkylation of Indos. The second one is catalytic asymmetric de-aromatic cyclization of tryptamines and tryptophanes. The third is catalytic asymmetric peptide Spengler reaction of tryptamines. And the fourth is catalytic asymmetric de-aromatic 2+A cyclizations of substituted Indos. There are some challenging issues in the chiral endochemistry, such as limited reaction partners, limited reaction types, constructing axially chiral Indos, chiral Indo-fused scaffolds, and spiral scaffolds. To confront these challenges in chiral endochemistry, our group developed a new unique strategy of designing and developing platform molecules and organocatalytic asymmetric reactions. By this strategy, we have synthesized a wide range of chiral Indo derivatives, such as Indo-fused 5-membered, 6-membered, and 7-membered rings, axially chiral Indo-based scaffolds, and tetra-substituted Indo derivatives. First, let me introduce the design and application of Indo-based platform molecules. Our group designed 4 kinds of Indo-based platform molecules. They are indoleo-methanol, heteroaryl Indos, 3-alkyl vinyl Indos, substituted Indos, and oxy-Indo derivatives. By designing these platform molecules involved catalytic asymmetric reactions, we have synthesized a variety of chiral Indo derivatives. The first kind of platform molecules is indoleo-methanol. The design idea is introducing hydroxymethyl group to the indolene and modulating the position of the hydroxymethyl group. As shown here, indoleo-methanols can be easily activated by chiral Bronsted acid to generate different cation intermediates after dehydration. In addition, by modulating the position of the hydroxymethyl group and incorporating different I1 group, these indoleo-methanols have controllable, diversified reactivity and reactive sites. So based on this idea, our group designed several indoleo-methanols. Here, I would like to introduce the most popular one, 2-indoleo-methanol. This kind of indoleo-methanol have 2 unique features. One is carbon-3 unplanned reactivity. Another is carbon-3 dual reactivity. At first, we discovered the carbon-3 unplanned reactivity of 2-indoleo-methanol. That is to say, in the presence of chiral Bronsted acid, the carbon-3 position of 2-indoleo-methanol will change from nucleophilic to electrophilic, therefore undergoing electrophilic substitutions and cycloadditions. Later, we also discovered the carbon-3 position of 2-indoleo-methanol can also display nucleophilicity to undergo nucleophilic cycloadditions. So, based on the unique reactivity of 2-indoleo-methanols, we have designed a series of catalytic asymmetric reactions of 2-indoleo-methanols, therefore constructing axially chiral Indo framework and Indo-fused chiral scaffolds. Here, I would like to give several examples. The first example is constructing axially chiral Indos. It's well known axially chiral biarrows are privileged scaffolds for chiral catalysts and ligands. Particularly, binapsal scaffolds constitute the core structures of numerous chiral catalysts and ligands, such as bino and bino-derived chiral phosphoric acid. However, in sharp contrast, axially chiral indole framework as a new kind of axially chiral scaffolds have scarcely been investigated, but with promising applications. The indole will bring some unique features to axially chiral scaffolds, such as changing electron density, modulating the steric congestion, and forming hydrogen bonding activation. Nevertheless, there are also some challenges in constructing axially chiral indole framework, such as remote author groups, lower rotational barrier, and unstable configurations. So it has become an urgent task to develop powerful strategies for constructing axially chiral indole scaffolds. To fulfill this task, our group designed a new strategy for constructing axially chiral indoles, while the carbon-3 unplanned reactivity of 2 indole methanol. In detail, we utilized the 2 indole methanol to react with a backing nucleophile in the presence of chiral bronzed acid. Due to the steric congestion around the axis, this class of axially chiral indole framework would be constructed. So based on this idea, we utilized the 2 naphthals as competent backing nucleophile and chiral phosphoric acid as a suitable chiral bronzed acid to undergo nucleophilic addition with 2 indole methanol, therefore constructing axially chiral indoles with high configurational stability. And this cover picture illustrated that we brought a new member to the family of axially chiral compounds. The second example is constructing chiral indole fused 7-membered ring via 4+3 cyclo additions. And in this design, we utilized the carbon-3 nucleophilicity of 2 indole methanol to react with in situ generated orthoquinone methydes. In the presence of bronzed acid, a nucleophilic addition between the 2 substrates occurred, and a subsequent intramolecular cyclization occurred. Therefore, constructing this chiral indole fused 7-membered ring. Another example is constructing axially chiral alkene indoles while designing 3-alkynyl 2 indole methanols as the platform molecules. And in this design, we introduced an alkynyl group to the carbon-3 position of 2 indole methanol, therefore making these 2 positions electrophilic. In this design reaction, we utilized the 2 naphthals as dinucleophile to react with this kind of new indole methanols to undergo 4+3 cyclization, therefore constructing axially chiral alkene indole scaffolds with simultaneously construction of a 7-membered ring. In addition, we performed theoretical calculations. It was discovered in the presence of chiral phosphoric acid, this kind of 3-alkynyl 2 indole methanols transformed into a lean iminium intermediate. And this cover picture illustrated that we designed this new strategy to construct these intriguing frameworks, just like Nuwa used the 5-color stone to mend the sky in the mythology of ancient China. The second type of platform molecules is heteroaero-indole, which was designed to construct axially chiral indole scaffolds. The design idea is introducing heteroaero groups to the carbon-3 position of the indole ring. And as shown here, this kind of platform molecule has some structural features. One is the carbon-2 position of the indole ring is nucleophilic. The second is the ANH group can be easily activated by chiral bronzite acid. In addition, there is an also Bucky group in the heteroaero ring. So when this class of platform molecule react with the Bucky electrophile in the presence of a chiral bronzite acid, an initial selective substitution or addition reaction would occur while a dynamic kinetic resolution process, therefore constructing axially chiral heteroaero indole scaffolds. So based on this design, we utilize the different heteroaero indoles to react with different electrophiles and constructed different heteroaero indoles, such as 3,3-bis indoles and 3-aero indoles. Notably, in these two structures, both axial chirality and central chirality have been created. And in this cover picture, we utilized a story in Chinese famous novel to illustrate the creation of this intriguing 3,3-bis indole scaffold. Very recently, we also utilized this kind of 3-aero indoles as 1,2 dinucleophiles to undergo 2+3 cyclizations with propagylic alcohols as 1,3 dielectrophiles in presence of chiral bronzite acid, therefore constructing axially chiral aero parallel indole frameworks in excellent stereoselectivity. So this approach not only provides a new strategy for constructing axially chiral indole-based framework, but also offered a new kind of axially chiral scaffolds bearing multiple chiral elements. More importantly, this kind of scaffold can be derived into chirophosphine, which have showed their preliminary application in palladium-catalyzed asymmetric reactions. The third kind of platform molecules is 3-alkyl vinyl indoles, which was designed for constructing chiral indole-fused heterocycles. The design idea is introducing LQ group and vinyl group to the indole ring. In detail, the installation of the LQ group to the carbon-3 position of the indole ring is to decrease the nucleophilicity of the carbon-3 position of the indole ring, therefore increasing the nucleophilicity of the vinyl group. In addition, the installation of the vinyl group to the carbon-2 and carbon-7 position of the indole ring is to make the vinyl group close to the NH group, which is easily activated by chiral bronzite acid, therefore facilitating the control of the initial selectivity. So, based on this design, we utilized 3-alkyl vinyl indoles as electron-rich olefins to undergo a series of 2+N cyclizations, therefore constructing different indole-fused rings. Here, I would like to introduce one example of oxidase-aldehyde reaction. And in this reaction, we utilized 3-alkyl vinyl indoles as dienophiles to react with in situ generated oxidines on the catalysis of chiral bronzite acid. In the proposed activation mode, chirophosphoric acid simultaneously activated both of the two substrates, therefore generating 3 adjacent stereogenic centers with high selectivity. The fourth kind of platform molecules is oxy-indo derivatives, which were designed for constructing spiral or tetrasubstituted oxy-indos. The design idea is converting indo into oxy-indo derivatives by oxidation and introducing functional groups. And these oxy-indo derivatives can easily undergo catalytic asymmetric cyclizations in the presence of chiral organocatalysts, therefore constructing different spiral oxy-indos and tetrasubstituted oxy-indos. Another example is the application of oxy-indo-based stearins to access axially chiral frameworks by the strategy of catalytic kinetic resolution. The design is based on the consideration that this agonal group in this platform molecule can act as a reactive site to undergo initial selective analysis with other electron in the presence of chirophosphoric acid via kinetic resolution process, therefore constructing two kinds of axially chiral oxy-indo-based stearins with high stereoselectivity. Notably, this class of oxy-indo-based stearins have proven to be privileged scaffolds for catalyst design. Later, I will introduce its application. The above introduced are 4 kinds of platform molecules and their applications in synthesizing chiral-indo derivatives. During our investigation, we also performed investigation on the mode of cooperative catalysis. For example, we established a new cooperative catalysis of chiral-protosyl acid with HFIP. By this new class of cooperative catalysis, a 3+3 cyclic addition of 2 indolylmethanol with nitrons have been established to construct these indofused 6-member rings in high stereoselectivity. The control experiment discovered that the addition of HFIP could greatly improve the yield and the initial selectivity. To understand the role of HFIP, we carried out the theoretical calculation. In the key transition state, we discovered HFIP simultaneously formed multiple hydrogen bonds with both chirophosphoric acid and the 2 substrates, therefore helping chirophosphoric acid to control the reactivity and the initial selectivity. So this approach not only developed a new mode of cooperative catalysis, but also constructed chiral-indo-fused 6-member rings in high stereoselectivity. So based on these approaches, we have synthesized more than 60 classes and more than 1,000 new chiral-indo derivatives, therefore providing a compound library for biological evaluation and catalyst development. For example, we carried out the biological evaluation on some of the products and discovered some products displayed potent cytotoxicity toward some cancer cell lines. In addition, we also developed axially chiral-indo-derived new catalysts, and this kind of oxy-indo-based stearin-derived chiral organocatalysts or ligands. And these catalysts or ligands have become commercially available in the company of Death Cell Chiral Technologies. Then here I would like to give a recent example from our group. In our previous work, we accomplished the synthesis of actually chiral oxo-indo-based stearins. So based on this work, we considered this amino group can be utilized as a reactive site to introduce a functional group such as thiourea tertiary amine group to synthesize a class of new chiral organocatalysts. And this kind of new organocatalysts has some characteristics such as efficient synthetic route, multiple chiral elements, and multiple activation modes. Then we utilize this kind of new organocatalyst to catalyze the 2+3 or 2+4 cyclization of this kind of imine with cyclic anhydride. And this reaction successfully constructed these 6-membered rings in excellent diastereal and inertial selectivities. To understand the role of this class of new organocatalysts, we carried out theoretical calculations. And in the Kiss transition state, we discovered the oxo-indo-based stearins formed several hydrogen bonds with both of the substrates, therefore making these chiral organocatalysts look like a chiral pocket, therefore facilitating the formation of multiple hydrogen bonds with both of the two substrates and controlling the inertial selectivity of the reaction. Here, I would like to show a very recent example to construct nitrogen-nitrogen actually chiral indos. And in this work, we utilized a new strategy of de novo ring formation to construct this new class of actually chiral scaffold. In this reaction, we utilized nitrogen amino indos as platform molecule to undergo Parnell reaction with 1,4-diketones, therefore constructing this new class of nitrogen parallel indo scaffolds. In addition, this strategy can be utilized to the synthesis of actually chiral bispirals, and some products have displayed potent cytotoxicity against tumoral cell lines. More importantly, this class of actually chiral scaffold can be derived into new organocatalysts and have found their preliminary application in asymmetric catalysis. Okay, in summary, based on the strategy of designing and developing platform molecules and their involved organocatalytic asymmetric reactions, we have synthesized a large number of chiral indo derivatives. To give an in-depth understanding of the reaction, we also carried out the investigation on the reaction mechanism and cooperative catalysis. More importantly, we also performed the investigation on their biological activity and catalyst design, which will be helpful for discover more applications of chiral indo derivatives. Finally, I would like to express my sincere thanks to my advisors, collaborators, group members, and foundations. Without their help and the persistent efforts of my students, we could not accomplish these works in chiral endochemistry. Thanks a lot for your kind attention.
Thank you, Professor Shi, for your very great talk. Excellent chemistry, extraordinary library, beautiful molecules, and selectivity, and a gorgeous cover picture. I love it.
Thank you.
Yeah, here we have got some questions. Here, okay, this one is English, so I'm going to speak English. The next, I'm going to talk in Chinese because that's in Chinese. So the first one was that it's great work. May I ask if you have ever tried those great methodologies to other substrates like Chiral and derivatives?
Okay, it's a very good question. Yes, we want to try the same strategy to other heterocycles such as Chirals and furans, but currently we haven't accomplished very good results, and it's our future project. We will extend this strategy from Indo to other 5-membered heterocycles. Thank you.
Great, thanks. Okay, next I'm going to speak in Chinese.
Okay.
石老师，就是您第14页上面，它上面有很多，就是有 NH， 有 OH， 然后还有 cation。然后您这 propose 就是有一个那个 selectivity。然后我想问的是，就是这个是怎么 control 的呢？就是它因为有不同的氢键作用力，然后它的那个氢键强弱之间有什么关系吗？
就你这个问题也很好，问的是第14页吗？
对，您可以 share 一下您的那个 PPT。
好的，我再 share 一下。我刚才看第14页，好像和这个问题不是很
不太一样是吗？
对，我再看一下。
我看一下是不是？
现在能看到我共享的屏幕吗？
是的，不是下一页上应该是。
他问的问题是，就是说这个怎么控制下一页？感觉也不是，是不是第4？
是这一页，15页是15页，对，我看它这有一个截图，因为是说，
是第15页。
对，您这有。
他的问题是，怎么控制？能够再简单的？
好像不是这一页啊。
对，我觉得
有一个机理的那一页应该是。
可能是不是这一页？我推测。就是这一页，
对，是这一页，是的，应该是这一页。
活性就是怎么来控制它什么时候是碳3的极性反转，什么时候又是碳3的亲和性。
对，
这个问题其实是非常好的，因为我们后来呢，其实也是通过了理论计算，就是也解释了为什么它有时候能够显示出碳3的这种极性反转的轻电性，那么有时候能显示出亲和性。当然，这个观众的问题主要是怎么来控制它们何时显示什么性质？那我们认为就是要看另外一种反应物它的性质，就是另外一种反应物，比如说这个地方同样是一种一头连氢电，一头连氢核，这个也是的。但是对于这种多反应活性中心的这个反应物呢，我们就看它有时候在反应中，它更倾向于是先接受进攻，还是它先进攻别人所以在我们发现就是说具有当这个2吲多甲醇具有亲和性的时候，另外一种反应物基本上都是很容易接受亲和试剂进攻的例如说磷亚甲基苯醌所以这个控制呢，我们还主要是从控制，就是说相当于改变另外一种反应物来实现对反应的2吲多甲醇这种性质的改变当然这个这位不管是这位学者吧，他的这个问题呢，可能是想如果说能够对同样的一种反应物能够实现它有时候显示出亲和，有时候显示出亲电，那是更好了。这个也是我们希望做的，但是我们想呢，可能有可能因为根据理论计算结果呢，可能这个手性布朗斯的酸的强弱以及空间位组有可能是对2吲多甲醇它的这个反应性进行一定的调控，但是目前呢，我们还没有很好的实现对于同样相同的2种反应物就能够实现这2种性质的调控目前就是回答到这里谢谢这个问题。
是的，很精彩，这种选择性控制很有趣。而这里我们还有一个问题是，施文老师您好，我想问一下，轴手性吲哚类化合物相比常见的轴手性连氖有什么特殊的优势，以及吲哚的5圆环相比氖的6圆环互为邻位的2个键角度增加，感觉这会造成一些不利影响，请问一下实际情况是怎么样的？
这个问题也是非常好，是的，就是这个这位学者他也是问了这个到底轴手性吲哚骨架和通常的这个连氖相比有什么样特点？这个呢，我们认为呢，就是因为它是一个5圆环，所以说呢，它可能是在空间位组上，它可能是由于这个问题里也讲到了，由于它的这个2面角改变，所以说它的这个稳定性，就是构型稳定性，在多数情况下呢，可能是没有这个连氖高的。但是呢，我们也可以通过引入其他基团来增加它的位组。 所以我觉得这个银朵轴手性骨架它最主要的这个优势和特点呢，我们认为呢，就是说它首先它是负电子方环，那么由于银朵的负电子方环，它可能会对这个催化剂它本身的这种催化活性来带来一定的影响。另外呢，由于银朵它是具有这个氮氢集团，那么氮氢集团呢，它可以与一些反应物呢产生氢键的作用，所以这样呢也有可能就是对活化反应物这个过程当中提供一些优势。当然这是我们的一些设想，当然我们现在也是在摸索，因为我们是设计开发了一些含有银朵母核的轴手性催化剂，但是目前这些催化剂它的这个优势，和它的优势的根源是什么？我觉得我们可能还需要进一步阐述，但是我们还是有信心，就是觉得这一类新型的轴性骨架一定能发现它更多的这个用途。谢谢。
是的，谢谢石老师，未来无限可能。咱这还有一个问题，就是请问一下石老师，羟基能换成其他离去基团来调整底物范围吗？
这个问题也非常好，我感觉问问题的老师和同学们都是非常在行，因为这个羟基是应该是可以换成其他基团的。实际上我们之前课题组也曾经合成过，但是呢我们就是没怎么用，其实我们是很想把它再换成其他的一些基团，这样呢就不一定非得在酸性条件下来发生反应了，因为现在是羟基基团它是容易被布朗斯的酸活化脱水，那么如果换成其他基团，它有可能在碱性条件或者其他条件适用，那么就有可能给这种平达分子带来更广阔的应用前景，所以这也是我们后面想做的，就是不局限于这个银朵醇类，就是把这个纯羟基可以换成其他的这个离去基团。谢谢。
好嘞，行，谢谢施老师。因为咱们时间有限，咱就先提3个问题。大家要是有什么其他问题，可以在留言框里面打出来，我们稍后会分享给施老师，然后在后期回复给大家，好吧？谢谢大家。Okay, then our next speaker is Professor Peng Wang from Shanghai Institute of Organic Chemistry. Peng obtained his bachelor degree in chemistry with honors under the supervision of Professor Jun'an Ma at Tianjin University in 2007, and obtained his PhD degree in organic chemistry under the supervision of Professor Yong Tang at Shanghai Institute of Organic Chemistry. He then moved to the Scripps Institute and conducted his postdoc research with Professor Jinquan Yu, where he focused on ligand-accelerated region-selective CH bond activation and non-directed CH functionalization. In early 2018, Peng started his independent academic career and joined SIOC as a full professor. His research focuses on transition metal catalysis and the main group chemistry. Professor Wang is our special guest today, and he is going to talk about his work on the synthesis and application of silicon stereogenic functional organosilanes. Peng, thank you very much for being here. All yours now. 王老师，您静音了。
Oh, sorry. So thank you, GT's kind introduction. I'd like also thank all editors' invitation to this event. So I'd like to talk about the functional organostatic chemistry today, especially the synthesis and the applications of silicon stereogenic organosilanes. So at the very beginning, I'd like to simply introduce the organostatic chemistry. So silicon is a member of group 14 in the periodic table below the carbon, and it's the second abundance element after oxygen in Earth's crust. In comparison to the carbon, silicon element has a smaller electron negativity and a bigger radius. The carbon-silicon bond is normally longer than this carbon-carbon bond and weaker in bond energy. This is why the nature normally chooses the carbon as a basic component for the form the organism. And also, so far, there is no organosilicon compounds in nature. Since the first synthesized the organosilicon compound in 1860s, organosilicon compound has been widely used in the field of organic synthetic chemistry, medicinal chemistry, and material science. As a synthetic precursors, organocyanins have been found in many name reactions, such as the Patterson reaction, Mukayama-Aldo reaction, Hayama-Coupling, and also, of course, thermal oxidation reaction. So, also as a basic element in the substrates, the silicon also being found in many bioactive molecules and materials. In industry, the widely used organocyanins are the polysiloxane, which have been utilized as the silicon oil, silicon tubes, or sealants on a large scale or amount. Silicon also can act as a coordination site to the transition metal, which can further enhance the reactivity of those metal catalysts. We all know the chirality is the one of the fundamental character in nature, and also normally the different enantiomers have different bioreactivities, especially when after this thalidomide tragedy. This tragedy significantly pushed the scientists to look into the different properties of the enantiomers, and also significant the progress have been made in the field of asymmetric catalysis. So, in compared to this carbon-centered chirality, the silicon stereogenic chirality is much less mentioned in the literatures. And the carbon-centered chirality normally rely on the transformations of carbon-carbon or carbon-hydroatom double bonds like arenes, alkenes, or carbonyls. Due to there is no stable carbon-silicon double bond available, so to construction those silicon stereogenic chirality is much challenge. And due to the bigger atom radius and the longer carbon-silicon bonds, so the well-developed strategy and the catalyst system for constructing those carbon-centered chirality might not be suitable for constructing those silicon stereogenic chirality. And most important, because there is no silicon compounds in nature, organosilicon compounds in nature, so there is the nickel precursors for constructing those functional materials, molecules. So to us, this provided us a huge opportunities to develop new strategy and a new catalyst system, which is particularly suitable for construction of silicon stereogenic chirality. And also along with the development of those new methodologies, we will develop a series of structural diverse organocyanins with different functionalities. If you look into those well-known silicon-containing molecules, or of course including those bioactive molecules and materials, there is no commercial available silicon stereogenic molecules in those compounds. It is another basis for us to develop new kind of silicon stereogenic chiral materials, chiral drugs, and chiral reagents. So today I will show you guys about several examples, or in our group, we are focused on developing new kind of synthetic methodology for the construction of silicon stereogenic chirality and the synthetic application of those functional compounds. The first story I want to show you is the cyclic monohydrocyanins. The silicon stereogenic monohydrocyanins have been used in synthetic chemistry as a chiral auxiliary, chiral reagent, or magnesium probes. Back to 2008, Professor Ostrich have mentioned that the monohydrocyanins can be used as a synthetic reagent for transfer for the construction the chirality via the intermolecular or intramolecular carbon to silicon to carbon chirality transfer process. And also most important is those silicon hydride compounds could serve as a versatile precursors for constructing other type of silicon stereogenic organocyanins, while the stereo-specific silicon hydrogen transformations. They well known, while they use the monocytosilence belongs to those kind of constrained cyclical monohydrosilence. Those monosilence could be synthesized while the multiple steps and finally by the chemical resolution with the stoichiometric Chiral reagent. So we're wondering those kind of chiral might be synthesized while the transition metal catalyze the intramolecular hydrosilylation reaction. So when we're screening a notable transition metal and the chiral ligand, we're lucky to find the rhodium catalyst with the biphosphate ligand could achieve this goal. We finally found the quinoxP ligand could give high DR and high EE. Of course, the Josephus also can give the high EE with this reaction, but with a slightly lower diastereomer selectivity. This reaction shows both substrate scope and also further high efficiency. Under our optimal conditions, this reaction can finish in 5 minutes at room temperature. And also when we run this reaction at a large scale, the catalyst loading could be reduced to 0.1 more %. The scope of this reaction is rather bold. The substitution on the silicon, no matter it's iron group or alkyl group, all could give high DR and high initial selectivities. And also the substitution on the backbone iron group, no matter it's electron rich or electron donation, all could give us quite high stereo induction. But notably, if the substitution is at the alpha position to the alkenes or at the alpha position to the silicons, they all can provide the high diastereomer selectivity and the initial selectivities. We also check the substitution on the alkenes. We found that the alkene could be the alkyl group, Wiley group, or even the phenol group. More delight, this protocol could also be applied to the synthesis of a few the 6-membrane monohydrosilence with high EE and high radial selectivity. The radial selectivity was generated from the hydrosilylation events. They can form the 5-membrane and the 6-membrane monohydrosilence. But in this case, under our optimal conditions, we only can observe the 6-membrane monohydrosilence. Of course, work with Professor Peng Qian in Nankai University, we got a chance to look into the detail of this reacting mechanism. So we found that our reacting basically is undergoes the Chiral mechanism. That means the alkenes is inserted to the rhodium hydrogen bond first. And also through the DFT calculation, we finally figure out the initial determinant step is the rhodium, the oxidative addition of the silicon hydrogen bond with the rhodium catalyst. So basically the decimation of dihydroxy organosilence determines the initial selectivity. So the result product also could be transferred to other tetral substituted organosilence with high initial selectivity. This product could also be transferred to chiral alcohol under the typical, thermo-oxidative conditions. So our story I want to share is the synthesis of this silicon-centered spiral cycles. So we all know the spiral cyclical chiral compounds have been used as a chiral ligand for a long while, for a long time. Especially Professor Zhou in Nankai University have developed a series of spiral-based chiral ligand, which have being used in many asymmetrical transformations. And thanks to those seminal contribution, so those type of chiral scaffold have been treated as one of the privileged scaffold in asymmetric catalysis. Of course, in addition, Professor Dean in SLC also demonstrated the SKP could serve as both the efficient ligand in asymmetric catalysis as well. So before 2020, there is no example of ligand design based on this silicon-centered spiral cycles. in comparison to this carbon-centered spiral cycle, we feel this silicon spiral cycle have some like unique properties. For example, those like silicon-based spiral cycles, they normally have the vertical and rigid configuration, and also due to the vertical configuration of these two phenol rings, so the coordination side of two hydroatom normally have longer distance than those ligands with the carbon-centered spiral cycles. And also because silicon is more electron rich, so makes those ligands slightly electron rich than those carbon-centered spiral cycle based ligand. So of course, if you want to design some like a new type of chiral scaffold for asymmetric catalysis, that also require those ligand scaffold must be synthesized easily. So this slide I just show more detail about the bond characters of spiral stellar cycles. In comparison to this spiral scaffold, we can say the silicon carbon bond is longer than those like a carbon-carbon bond. Of course, the dihedral angle normally is like around 90 degrees centigrade. For this carbon-centered spiral cycle, the dihedral angle is around 64 degrees, and also the oxygen the distance in sp scaffold is much longer than that in spiral. So it's 5.2 angstrom. But we also check other type of silicon centered spiral cycles. We found with this SPO style scaffold, the oxygen distance is quite similar to its carbon-centered spiral cycle analogs. So those different characters indicate those silicon-centered spiral cycle might have great potential in development some like a low chiral catalyst or low ligand for asymmetric catalysis. So this slide just show one more information about the structural difference between the carbon-centered spiral cycle or silicon-centered spiral cycles. So for this spiral, as we mentioned before, this like dihedral angles is around like 64. But for all those like spiral-centered hydrocycles, we can say they all hold a vertical configuration. Those totally different configuration might result totally different properties or reactivities in further asymmetric catalysis. Although those silicon-centered spiral cycle posted great potential in asymmetric catalysis, the asymmetric synthesis those kind of structure is much less mentioned. So the first example, for the synthesis of chiral spiral stellar cycles was reported by Tamo in 1996. Their group only show one example of this case with high EE. And also, Takei group have developed rhodium catalyzed CH bond dehydrogen native cyanidation reaction for construction of chiral spiral stellar cycles. So they can get, in this case, they can get 81% EE, and also for sp3 CH bond, they can only get 40% EE. So we were wondering maybe those type of spiral silane diene structure could be easily synthesized by the transition metal catalyst, the double hydrogen cyanidation reaction. So we finally get this starting material, this diene starting material. We found that with the rhodium as a catalyst, with the diphosphine ligand, we could efficiently get the spiral stellar bienal structure with high E and high diastereomer selectivity. We want to mention that use R-quinoxP as a ligand, the E value is quite high and the diastereomer selectivity is excellent as well. But if we use R-dufos as a ligand, we could also get another enantiomer with high E and high diastereomer selectivity. That means we could get a couple of enantiomers by switching the different chiral ligands. As those structures might also have potential applications in material science, we also check the scope of this reaction. We found the substitution on the alkenes also, as well as the substitutes on the RNs, all gave quite high yield and high chiral induction. Most important, if we have the substrate with the mesoscale group at the ortho position of the silicon, we can also get high EE and high diaspora selectivity. Those compounds can be used as a precursor for constructing the SP cell. So with the newly developed methodology, we could start from the 3-bromide to 3-hydroxy benzoaldehyde. We can easily make those like a precursor for ring open process. Use our methodology, we could run this reaction over 50 gram scale, get the desired sp7 methyl ether in high yield and high initial selectivity. In most of cases, initial selectivity is over 90%. So we further try to demonstrate the synthetic application of this ligand scaffold. So we try to synthesize the phosphoramidite ligand. So this ligand can be easily synthesized starting from the initial pure sp cell in one step. We, as you can see in this slide, in most of cases, the yield is around moderate to perfect. And also we previously we check the synthetic application of those ligands in asymmetric catalysis. As shown in this slide, we found that our silicon center spiral cycle based ligand can show a slightly better results in comparison to the carbon center based ligand. So in this rhodium catalyzed asymmetric hydrogenation reaction, also in this palladium catalyzed carbon amination reaction, we found that our ligands show better reactivity. So use our ligand, we can run this reaction at room temperature. However, with the carbon-centered ligand scaffold, this reaction needs to run at 19 degrees centigrade. So with this like a SP cell, we have demonstrated a series of the novel cover ligands, like monodentin ligands and bidentin ligands, like the bisulfurone ligand and bisphosphorin ligand. We also can make this phosphoric acid, which could be used as an organocatalyst in asymmetric catalysis. So encouraged by those results, we thought all kind of the silicon, centered spiral cycle might be a potential scaffold for novel ligand development. So we also try to synthesize a novel 6 spiral 6 type of SPO cell molecule. This one can be easily made from the 3-methoxy diphenyl ether or this dibromide compound. So we can synthesize this like a methyl ether in high yield, and finally demethylation gets the racemic SPO cell. This one can, after the chemical resolution with the chiral reagent, the methyl group, we can get the initial pure SPO cell. So this kind of ligand scaffold could also be used in asymmetric catalysis. For the asymmetric hydrogenation, we can also get quite high initial selectivity. They can also be used in copper catalyzed conjugative addition reaction, get like 91% EE. In addition, when we use this ligand in palladium catalyzed intramolecular carbon amination reaction, we can also get like 83% EE. So far we have demonstrated the silicon centered spiral cycle can be used as a versatile platform for develop like a new chiral ligands or catalyst. So the most important is if you want to use those novel ligands to develop some like new reactions. Here I just want to show one example of the synthetic application of those ligands. So like I presented in this slide, we demonstrate our ligand can be used in hydrosilylation of the amines. So hydrosilylation of amines could be same size like a atom economic method to construct the vinylsilanes and the anilsilanes. And the 6 isomers could be formed in this reaction. So if you want to achieve the asymmetric hydrosilylation reaction of the amines, that means you need to control the chemoselectivity and the radioselectivity as well as the initial selectivity at the same time. So there are only 2 examples of the branch selective hydrosilylation reaction have been reported before. Montgomery in 2013 2013, they have demonstrated palladium HC carbon system could achieve the branch selective hydrogenation reaction with high radioselectivity. And Professor Zhang in Xiamen University also demonstrated liquid system could achieve the hydrogenation of anions. But for this 1,1 disubstitution anions, they can only get like 84 to 16 like radioselectivity. The only example of the asymmetric hydrogenation of anions have been reported by Tang. As you can see with this like a monodentate phosphorus ligand, so with diphenylsilanes, they can get like very high yield and moderate initial selectivity. But the radioselectivity is quite high. When they increase they use bulky triphenylsilanes, so they can get the initial selectivity increased to 90%. However, this radioselectivity decreased to 1 to 1.2. This example also showcases the challenge of this hydrogenation, asymmetrical hydrogenation of anions. Then you need to simply control the radioselectivity and the electroselectivity at the same time. So we try this reaction with liquid system. So with while they use the purely oxygen system, there are no reaction for this reaction. We also found that the diphosphorine ligand is suitable for this reaction to get high yield. But the commercially available BiLab or DPE systems, they normally give us in unsatisfied radioselectivity and electroselectivity. So interestingly, when we use our ligand, our scaffold SP-cell derived phosphine ligand, we can get quite high yield and also the linear selectivity. Interestingly, when we extend this, try some like a biphosphated ligands, we can say the electroselectivity could be increased to 50%, and the radioselectivity is okay with like 4 to 1. We further modify this ligand with the R BiLab scaffold. We finally get this reaction with 94% EE and excellent diastereomer selectivity. So I just want to mention once again, this type of ligand is quite easy to make. We can start from the SP cell molecular and in the presence of base, we can synthesize this compound in one step with moderate to good yield. And also we got the crystal structure of this ligand to confirm the structure of this compounds. So under the optimal conditions, we also look into the scope of this reaction. We found that all kind of, so the reaction could compatible different electron donation and also electron withdrawing in iron group. And notably, if we have a terminal alkyl group, this reaction could selectively occur at the anion side. This reaction could also compatible with a few like a bulky dialkyl anions with this like this cyclohexyl group. We can also get like a 89% EE. Notably, this reaction could be used in mainly like hydrocycle containing substrate. This is not normal in asymmetrical hydrogenation reactions. We also evaluated the scope of our silanes. No matter it's our silanes or alkyl this reaction could give excellent radioselectivity with perfect the electron selectivity. Even for this longer chain alkyl group, we can also get like 87% EE. So the scalability of this reaction also demonstrated by running this reaction on 5 millimole scale. This reaction we can get the final product in 99% yield and 94% EE with excellent radioselectivity. The final product also is synthetically useful. We can do some transformations on silicon hydride. For example, with the Kubo catalyzed hydrogenation of this aldehydes, we can get this like a silicon stereogenic center with high DR. And also we do some transformations based on this alkene. We can do hydrogenation and hydroboronation to get a synthetically useful boron silicon compounds. So in summary, we have developed several new strategies and new methods for construction of silicon stereogenic borohydrosilanes and silicon-centered spiral cycles. We also try to demonstrate the synthetic applications of those silicon-heterogenic compounds, such as this like a silicon-centered spiral cycle, could be used as a versatile platform for new ligand and new catalyst development. We also demonstrate the synthetic application of those functional silicon-containing ligands in asymmetric catalysis. Finally, I'd like to thank all my students for hard working and all financial support. I also finally thank GT or Anne for support. Last year, we invited us to publish a review paper in EJOC. This basically is our first review paper from our group. So thank you for all your attention. I'd like to answer any questions. Thank you.
Thank you, Professor Wang, for your interesting talk, for telling us there's another possibility designing new ligands and for applying to the reactions with way more better reactivities. Thank you very much. We have received many interesting questions. Okay, so I'm going to start with the first one. 请问王老师，硅基配体二面角的大小更多的是影响反应效率还是手性质呢？
这是一个很好的问题。实际上，在目前为止，这个硅基配体这个夹角，到目前为止，我们一个最基本的认识是，比如说，因为它的问题是要同时控制这个手性或这个活性，其实这个可能没有一个很直接的一个结论性的东西，可能在很多时候它同时对这个活性或这个手性诱导都有一个比较大的影响。当然，对于不同的单齿和双齿配体，它可能展现出的这个性能也不完全一致，尤其是在我们之前的这个八催化的这个，比如说对于这个八催化的方胺化反应里面，我们其实发现这个对于这个单齿的这个亚磷酰胺配体，我们发现对氢化反应里面其实手性也可以有所提升。当然，对于这个八催化的方胺化反应，我们也发现这个用这个硅螺环衍生的这个配体的，它其实对于这个反应活性也有比较大的一个影响。尽管目前为止，我们认为可能是由于它这个构象影响会更大一点，但是还没有一个更直观的一个证据。好，谢谢他提问。
谢谢王老师。那在第二个问题是，王老师您好，我看您后面的硅锑螺环配体主骨架和之前的碳骨架有哪些优势？能否做一些之前碳螺配体解决不了的反应？我想您后期的报道里面已经说解决了这个问题了。那您还有什么要补充的吗？
对，也不是完全是解决掉，我觉得这是一个我们可能课题组长期的一个任务吧，对吧？因为比如说我当时总结了一些，就是硅中性螺环现在相对于碳中性螺环的一个不同，最关键的一个是它构型上的一个改变，另外一个它这个配位原子之间距离会更远。其实更关键的是在这个螺环配位的过程中，实际上碳硅键更长之后呢，它这个夹角其实比碳中性螺环它要更柔性，反而不是我们最开始理解的更刚性。另外一个其实它更容易制备。至于它能不能用于解决一些全新的反应，我们在后面报告中我展现了一个这个列催化的这个氢光化反应。实际上我们也试过碳中性螺环，我们的结果大约要比它高10%几的这么一个手性诱导。更为关键的是，我希望能够后面吧，我们继续努力，能够更好的回答这个同学的问题，来告诉我们硅中性螺环相对于碳中性螺环有一些什么特别的一个地方，或者说能够有一些独特的地方，能解决一些更加重要的一些反应。好，谢谢。
谢谢王老师，期待您更多的报道，我们下次再继续讲这个问题。还有一个问题是，王老师您好，请问相比丁奎林院士的 SKP 配体，这两种配体点距离超长的，您的骨架有什么样的优势呢？如此长的配体点距离会不会与金属形成反位配体，甚至只能与其中一个配位点配位？
这个问题实际上是一个很好的问题，尽管我们现在研究的这个数据还不够多。丁老师这个配体骨架，它这个双棱之间的距离大约已经接近6点多了，对吧？其实是很远，但实际上在我们做成我们自己配体的这个双棱呢，是大约在5.8这个距离，就是我们后面这个稍等一下，不好意思，就是这个双棱配体，实际上大致这个距离是在5.8左右。所以说我们的这个配体之间这个棱间的距离是介于这个周麒麟老师和这个丁奎林老师这两个配体之间的。至于在我们的这个配体活动中，针对不同的金属有没有可能形成这种反位的，比如说假如说我知道这个类似于 Ramphos 对于有些配体配位的时候，这种 可能性，我觉得是有的，因为尤其是在我们这个碳硅键更长的时候，它这种配位模式实际上完全取决于可能这个金属与这个磷配体这个配位的一个强弱。至于它能够应用在这种特性能够应用在什么类型的反应里面，可能还有待于我们进一步研究。对，好，谢谢。
咱今天收到的问题很多啊，咱就快一点问。这里有一个英文的 Dear Professor Wang, are there any examples that chiral spiral ligands using silicon as connection port can achieve high inertial control while the spiral chiral ligand using common carbon as connection port cannot? Okay, 这是类似的问题了。
Yeah, I think that's a good question. We need a lot of work to confirm this silicon-containing centered spiral ligand could be used some like a unique reaction, which cannot use the carbon-centered ligand design. I can show one example. I can show more data with this unpublished reaction. So with our ligand, we can get that lighting 4% EE, but with this carbon-centered scaffold, the EE value is around like 10% less than us. So that also demonstrates the silicon-centered, spiral cycle might have some unique properties in some like reactions, but I'm not sure if that means. If you want to develop like a new ligand, that doesn't mean this ligand can do some others cannot do sometimes. But we hopeful we can find some unique examples to answer this question. Much better. Yeah, thank you.
Okay, thank you, Professor Wang. Okay, 这还有一个王老师好。最后一个反应，螺环和连氖哪个贡献大？
这个其实我们做过的。如果其实在这个例子里面，我们做过反构型的这个白裸，对吧？就是因为我们现在用的是2构型的白裸是最好的。其实反构型我们这也做过，反构型的白裸我们的EE值大约降低到50%左右。但是同时这个手心诱导这个立体决定的这个手心构型啊，它还是跟我们现在得到的产物的这个绝对构型是一致的。这就意味着这个中心的这个螺环中心的这个手心啊，可能对于这个不对称轻硅化反应，就是目前这个反应，它的贡献应该是更大一点。因为不然的话，如果说你改变就是外面这个白裸的这个构型，应该是对于这个手心诱导或者说对于它这个绝对构型会有一个比较大的一个影响。好
的，谢谢王老师。因为咱们时间有限，还有问题没有回答，就请王老师会后在框里面回答，好吧？在聊天框里面给大家回复。好，接下来我们介绍一下第3个主讲人。Our third speaker here is Professor Rai Wang from the Young Advisory Board of ChemCatChem. He is currently Associate Professor at the Chemical Engineering Department of University College London. Rai obtained his PhD in chemistry at Peking University in 2012. He then spent 2 years in Germany and worked as an Alexander von Humboldt Research Fellow at the Max Planck Institute für Kohlenforschung. In 2016, he moved to the United Kingdom and joined the UK catalysis community. He was appointed as lecturer at the University of College London at the beginning, and then was promoted as associate professor last year. Over the years, he has been actively engaged with the UK Catalysis Hub and the Diamond Light Source. His research mainly focuses on the time and space-resolved operando methods in heterogeneous catalysis. He has been awarded the Young Scientist Prize of the 16th International Congress of Catalysis. He is now serving the EPSIC using working group at Diamond Light Source and the EPSRC Strategic Advisory Team on Capital Equipment, the high-level group of the National Research Facility, and the Early Career Advisory Board of ChemCatChem. Today, Rai is going to talk about X-ray based in situ spectroscopy for oxidation chemistry. Rai, thank you very much for being here. Please take the floor.
Yeah, thank you very much for the nice introduction, and you can hear me, right?
Yes, great.
Okay, fantastic. So, yeah, thank you for this. And then now I would like to change the topic slightly from very advanced molecular chemistry into something we call the solid chemistry and heterogeneous catalysis. And I will start to introduce the techniques which we're using at the synchrotrons And I know that most of you have heard of that, but maybe have not been there. I'm currently actually sitting in a synchrotron in the UK. So I want to introduce what synchrotron can do, and then in particular for X-ray spectroscopy, what it can do in chemistry and in particular in catalysis. So I would like to start with the basic concept of how X-rays interact with matter, for example, like a solid, liquid, atoms, molecules. So back in 100 years ago, Albert Einstein discovered this photoelectric effect. When there's an electromagnetic wave exciting a semiconductor, they have this effect from the electrons, and this is how we get the solar panels. So this is how we get renewable energy. And later on, people also found that if you increase the energy of this electromagnetic wave into a very high energy region, which is the X-ray region, and then when the X-rays is interacting with an atom, just like exciting the atoms, it's basically interact with the electrons in the atom. And in this case, it's the oxygen atoms, an X-ray flow comes in like 1000 eV, and then the 1s electrons of the oxygen will be knocked out, and we are going to exit the atom, exit the materials, and can be collected by a detector. Of course, that quantifies the energy that carries by these electrons, and with the instant beam energy, then it's possible to determine what is the bonding force between these electrons and this atom. And this is basically what we call the bonding energy in the XPS. And we can use that to first identify which element it is, because oxygen and carbon have different bonding energies. And then we can also identify the oxidation state of the element. That is one of very few methods that we can use in the lab base to identify the oxidation state of the element in the material. But today I'm going to talk about something slightly more complicated. Just imagine that we have an electromagnetic wave is hitting an atom, and here I use a very nice example from my group. So we always studying with the copper cations, and copper 2+ cations is a very unique in the periodic table. It's a D9 configuration, and if you just go a tour around the periodic table, copper 2+ is the only D9 configuration cations you can find in the periodic table. Silver and iron and gold, they don't have 2+. So this is a very unique. It's a D9. That means that you have an empty orbit. You have a half-filled orbital here, which also causes the John-Taylor effect. Now let's look at if there's an electromagnetic wave hitting the copper atoms, what happens? So basically, the electrons in the copper can be excited. If the energy is strong, they can be excited outside the materials. But if the energy is not strong enough, then depending on the instant beam energies, the electrons can move in, for example, from the 1s orbitals all the way to these vacancies of 3d orbitals, and all from the 2p orbitals to 3d, or from the 3d to 3d. And of course, because this 1s, 2p, and 3d orbitals, they are sitting at different orbitals, the energy is different. That will mean that by exciting the 1s, 2p, and 3d orbitals, the energy of the instant beam is different. And I plotted here roughly the energy required here for the instant beam. So here is basically requires X-rays, and here is requiring about 1 eV, which is equivalent to the visible range. And this is what we call the absorption of X-ray. So basically, we absorb the X-rays, and one electron is excited to high orbitals or to continue. The experiment actually is very simple. So I think most of you have seen or have used the UV vis spectrometer. And basically, you have instant beam light, the intensity, which counts the number of photons in the beam. It's called I0. And passing through the beams, and then you can have some of them, of the photons absorbed by the materials, and some of the photons will be transmitted. And use I0 minus I, then you have this. Then you can calculate how many photons which is absorbed in your materials. By changing the instant beam energies, then you can know that the amount of absorbed photons as a function of the energy. And that is we call the absorption spectroscopy. Of course, it follows this Beer-Lumber rule, which means that there's an absorption coefficient here, the thickness of your sample, as well as the concentration of your sample. For example, if you're measuring copper, it means that how many copper cations or copper elements you have in the materials. So let's look at 3 absorption spectroscopy. And this is a typical UV spectroscopy of copper 2+. You can see the maximum absorption is about 8 nanometers. And by the way, although it's nanometers here, but is a spectroscopy, you can always relate this kind of x-axis into energy. You can translate into E equals to h mu, and then h mu equals to hc over lambda. And lambda is the wavelength. So this is equal to energy. Here is roughly about 1 eV, so it's about 1.5 eV. That is absorption, and this triggers the 3D to 3D transition. And by the way, because the copper 2+ cations like to absorb this type of red light, and that is always why when you have a copper 2+ in the solution, the color is blue, because the blue can be transmitted, while the red will be absorbed. And this is basically the valence transition. If you want to excite 2p electrons, then you need to increase the energy of your X-rays, and here we need to use 930 eV, and this is what we call soft X-ray regime. And this is also we call the copper L edge X-ray absorption spectroscopy. The atom L means that it's excitation of the 2p electrons. If you want to excite the 1s electrons, then you need much higher X-rays. So you need 9,000 eV, which is roughly about 10 times higher of energy compared to soft X-rays. So this is what we call the hard X-ray regime, and we call the hard X-ray absorption spectroscopy, and this is what we call the copper K edge, and K is equivalent to the 1s. So basically, we are exciting the 1s electrons. So this is the basic concept of the absorption spectroscopy. Of course, in the UV, it's quite easy because you just have a light, and you have a monochromator to change the wavelength of the light, and that's how you can get a UV. But for most of the lab-based X-ray sources, you can only have one single wavelength of the X-ray, or let's say that one single energy of the X-ray. So it's impossible to measure, to change the energy of the incident beam. And with that, you need something so-called a synchrotron, which is basically you have a circulation of very high energy electrons. They're traveling as a light at the speed of the light. And then you try to use the magnets to bend the electrons. And by bending the electrons, it will release energy, and energy is released as X-rays. And the synchrotrons offers continuous X-ray source with tunable energy. So basically, you can easily tune the energy. For example, in the beamline I'm currently sitting on, it can change from 2,000 EVs all the way to 25,000 EVs. And that's how you can do the absorption spectroscopy. It also have a very high flux. So per 1 second, there will be 10 to the orders of 11th number of photons coming from the beam. So it's a lot of photons. That's why we can detect them. Of course, synchrotron techniques are very expensive. For example, the ones in diamond cost about 300 million pounds, which is very expensive and large resource. The ring here will roughly take about between 900 to 3 kilometers. That's why there are only limited number of synchrotron radiations around the world, and mostly in the US, in Europe, and also in east part of Asia. In the China mainland, we currently have one in Beijing, and one in Hefei, and one in Shanghai. The fourth one, which is the fourth generation, which is also will be commissioned in Beijing, and there will be another one in Shenzhen and another one in Wuhan. There are also 2 small synchrotrons in Taipei. Okay, so with this, then what I want to introduce here, can I get rid of this one? Oh, yes, is how we can use X-ray absorption spectroscopy, somebody also called it ZAPS, to apply them in catalysis, and what we can do in catalysis. One of the most famous example, or actually one out of 5 papers in catalysis, will be reporting the single atom catalyst. And then to confirm that you have a single atom, you need 2 techniques. First of all, you need the TEMs to confirm that, okay, you have the single atoms, as here the platinum atoms, the rhodium atoms, and the platinum atoms here. So they are single atoms sitting there, not interacting with another platinum, palladium, or rhodium atom. And then you need the ZAPS, which in the extended range, then you can is related to the X-ray scattering between the 2 heavy atoms. And then, since we cannot find out the scattering between those rhodium and rhodium atoms in this case, then you can confirm that it's a single site. In addition to that, we can also measure the scattering between the rhodiums and the local coordination atoms. And in this case, it's a 4 chlorine and 2 nitrogen atoms. So then we can even determine what is the local coordination structure of this ruthenium. And this is a bipyridine compound of rhodium with 4 chlorine ligands. And this is the most widely applied X-ray absorption spectroscopy in catalysis. But today I'm going to show you something slightly different, a little bit more advanced, and I will give you 3 examples which focusing on determining the oxidation state of a metal cations during the reaction, determine the electronic structures of the metal cations and plotting the catalytic activities as a function of those electronic structures, and also as well as determine the local coordination environment of an active species that is in situ formed during catalysis. Most of them are applied for C oxidation, which is very simple chemistry. And in my group, we're also doing other oxidation chemistry, such as ammonia oxidations, as well as the selective catalytic reduction of the unknown. But this is also very basic use of synchrotron X-rays. There are way more examples we can find in literatures. For example, studying the difference between the surface bulking catalysis, the transient species that only have a milliseconds of lifetimes, the location of a metal cation in the lattice, the bound breaking and formation dynamics. So due to the time limitations, it's not possible for me to introduce them, but we need to be aware that this is definitely possible to use synchrotron X-rays. So our first synchrotron experiment is actually happens here where I'm sitting now. So it's a B18 beamline of the diamond that was back in 7 years ago in 2015. And at that time in the lab, we have this nice copper catalyst for C oxidation. It's very active, it's 20% of copper in cerium. And we set up an in situ electron paramagnetic resonance spectroscopy because the copper is a D9 configuration. It has a 1 electron spin. And we can quantify the copper 2+ in the catalyst as a function of time, and we're applying catalysis for different gas atmospheric conditions. And with 1% of CO, we see that the copper 2+ is reduced. But with APR, we don't know whether it's reduced to copper 1+ or it's reduced to metallic copper. And this is how the X-ray absorption spectroscopy kicks in, and it shows that, okay, it's metallic copper. And with that, we can finally write the part of the reaction equations, that is the copper 2+ plus a lattice oxygen reacting with CO to form copper 0, not copper 1+ and CO2. So this is basically the initial activation of the CO in the C oxidation reactions. And of course, it's very interesting that in the nitrogen, there's no oxidative species in the gas atmospheres, and you can see there's a still oxidation of the copper. We are quite interested in why this is happening. So that's why we applied operando ZAFs. That means that we are constantly measuring ZAF spectra. So for example, in these figures, we have the gas atmosphere here, and then each vertical line is the first derivatives of X-ray absorption spectroscopy as a function of time. So we are collecting a lot of X-ray absorption spectroscopy data. Initially, it's a copper 2+. When you have the CO there, you reduce to metallic copper. In the XRD patterns in situ, you can also see the copper oxide, copper 201, and into metallic copper. At the same time, you can also measure in cerium. So basically, just change the energies to 5,000 EVs, and then you can see that cerium 4+ is partially reduced to cerium 3+. You can also do in situ IR here, and do some to find the surface formation of the copper carbonyl species, as well as the amount of CO2 generated, which you can quantify. So anyway, combining these 5 figures, then we can confirm that the first reaction is this one. So copper 2+ react with CO to form copper 1+ and CO2. In the second steps, we're going to helium, and there's no oxygen in the gas phase. What we can find here is the copper 0, metallic copper, is slowly oxidized into copper 1+, which is also seen in XRD. And then at the same time, the cerium 4+ is reduced to cerium 3+. Combining these 3 figures, it shows us this reaction happens in the catalyst without the gases, so it's not involving the gas. It's the copper 0, metallic copper, reacting with the cerium 4+, forming the copper 1+ and cerium 3+. This shows nicely the redox properties of the support cerium can help the redox of the copper and to help perform the catalysis. And the third step, then that is basically facing the oxygen, and then the copper is oxidized to copper 2+, at the same time cerium is oxidized to cerium 4+. So this is the reaction taking place. So basically by combination of these 3 steps of separated reactions, then we can draw a general figure of how the electron transfers within the carbon oxidation cycles. So starting with the carbon oxide, which is the electron donor, let's say, for example, in organic chemistry, and the electrons will go to the copper to reduce the copper, and then can go to the oxygen to reduce the oxygen that forms CO2. So basically, this is called the direct pathways for copper catalyzed C oxidation. But it also goes to copper or cerium, and the copper pathway passes the electron to the ceriums, and the cerium then catalyzes the oxygen reduction reactions. And this is called the associated mechanisms that involving the redox path of both copper as well as the cerium. There's also an inhibition effect that the carbons can form the surface carbonate species, and that will also serve as an electron pool and they stay here, and then this will facilitate the oxidation reactions and will be the inhibition of the reaction. So by mapping that, by combination of multiple techniques together, then it's possible to understand the complete electron pathways within a single cycle of the C oxidation, how the electrons is passing from the CO all the way to the oxygen to form the CO2 through the different catalytic materials within a one single surface. So which is a very nice example to show how to apply synchrotron X-rays to understand the mechanisms of heterogeneous catalysis. And in the next example, I'm going to show you slightly more complicated nature of how cations sitting on the surface of catalyst. Our motivation is that if you have a bulk copper oxide, then it's a semiconductor for sure. So you have the valence band and conduction band. There's a band gap here. And then if you support the copper oxide clusters onto a cerium, as you go down the sides of the copper atoms, then initially you have a band structure. But if you don't have that many coppers, they have the orbitals coordinated together, then you have discrete orbitals, and then finally you have the molecular orbitals of the copper, which is of course interacting with the oxygen. So it's a molecular orbitals of copper and oxygen, and this is what we can call even in organic chemistry the homonummal. And this homonummal gap should be much higher than the band gap of the solid. This is our hypothesis. We need to prove it. And the way to prove it is to apply X-ray absorption spectroscopy. Remember in the beginning, I showed you a figure that we can excite copper 1s to 3D, but also excite copper 1s to 4p. Remember that the copper 2 plus is a 3D9 configuration. That means that the 3D9 is probably already the HOMO. And you can see that for the bulk oxide, the energy is here. And then for the atomic side, the energy is 0.7 EV lower, which will mean that you have a lower HOMO of the copper. Although we cannot directly see the LUMO, which is the copper 4s, but we can see the energies for p orbitals, and the 4p orbitals have a 2.2 EV higher energy than that of the clusters or metal oxide bulk. So with this, we prove our hypothesis, which shows that actually the atomic copper side on the cerium, because of this electron withdrawing effect of ceriums, have a lower the HOMO, and have increased energy of the lumos. We can even quantify the amount of the copper using APR, and then we can plot these quantify the ratios as a function of the real copper loading to show that actually at 1% you have most of the single side, so 80% of the coppers are single side, but after 1% then start to form clusters and diamonds. So how does this apply in catalysis? Here I show you everything below 1%, which they're almost a single atom catalyst. You can see that kinetic plot, which is called Alkenes plot, is falling into a single line. That means that they have exactly the same turnover frequency and exactly the same activation energy. As you increase the loading, then you have a different copper species because they're from clusters, diamonds, metal nanoparticles. Then the activation energy varies, and also the turnover frequency start to drop. What is important here is that we can even plot the conversion of CO as a function of the copper 2 plus single side API intensity, and it shows a quite linear relationship. On this side, this is the activity that we measured in a reactor. And on this side is actually the spectroscopy result we get out. So basically it's a nice correlation of the activity result with the spectroscopy quantifications. What we're also showing here is the plot of the turnover frequencies as a function of the 1s to 3D transition energy. It shows a negative relationship, meaning that you need a high 1s to 3D transition energy of atom of a single side to catalyze the CO oxidation. We are quite interested in why such a single side can activate CO and oxygen. That's why we apply this soft X-ray. So basically you can see the energy here is only hundreds of EVs for both copper and oxygen. So the most important figure here I want to show is that on this copper single side, it forms an eta oxygen species, which is like a peroxide species. They still have the oxygen-oxygen sigma bond, but they don't have the pi bond anymore. And this eta oxygen species is very active because it's like a peroxide, so it can activate the CO, and that's how the single side shows very active species. What is the structure of the single side? We then apply the KH, we can see it's very high EV, and then we can do the Zapf fittings to fit the coordinations of the copper. We found out that when there's one copper 1 plus, in the presence of reduction atmospheres, is one copper with 2 oxygen. So this is the copper species in the reduced form, and this is the copper species in the oxidative form. And during the CO oxidations, it's a rapid change between reduction form of the single atom and the oxidation form of the single atom. Such a dynamic nature of this single site catalyzed the CO oxidation. And this is also something that is not unique for copper serial. Recently, we also found that this is also possible to see that the HOMO and LUMO changes of copper over iron oxide. And then we can then also, doing this, our collaborators in Wuhan University help us do the DFT simulations to help us understand the nature of such a drop of 1:3D and such an increase of 1:4P. As you can show in here, that the d orbitals has a vacancy here, which is the vacant orbitals, and therefore the copper oxide is slightly higher. It's about 1 eV higher, which is exactly the same result we are seeing here in spectroscopy. And we can apply this type of catalyst for ammonia oxidation reactions. And again, we see such a nice plot that is the turnover frequency shows as a function of the 1s-3D transitions, and also the highest 1s-3D transition, which is the atomic side, has the highest turnover frequency, which is not a surprise, but we think this is kind of a general hidden rule in chemistry that while the HOMO of the single side is quite decisive in terms of the activation of molecular oxygen. And at the last, I want to use maybe 5 minutes time to introduce a little bit about how we can identify the transient active species and their local coordinators. So this is the part that's quite similar to organic chemistry, because we are using organic chemistry or Suzuki cross coupling reactions to make a polymer with the bipyridine ligands, and we use this bipyridine ligand to coordinate with a metallic coordinate ruthenium 3+ cations, as shown here. Each dot here representing a ruthenium 3+ cations. We show that it's oxidative rutheniums, and initial coordination structure from the ZAF is 1 ruthenium, a bipyridine ligand with 4 chlorine. And this species is unfortunately not active at all for CO oxidation. We need to activate it. The way to activate it is to pass it through the catalyst with a CO, mixture of CO and hydrogen. We see an HCl formation, and then we also see in the drifts in situ IR the formation of the ruthenium cation carbonyl species, which is shown here. And then we have the ZAF features fitting the spectrum, which is a ruthenium, 3 chlorine, and 1 CO and 1 pyridine. So basically, we identified that the activation reaction is this reaction. So we have a proton here to balance the charge. We have the CO here, and then it forms this type of structures with ruthenium with bipyridines, CO, and chlorine. And CO is actually here instead of here, determined by the R spectroscopy. In the second step, we try to have the hydrogen to activate it. You can still see some of the HCl release, and then you see a double features here in the IR. And checking the literature that we also with our ZAF result, we identify is this type of isomers. So basically it's a ruthenium, 2 CO, 2 chlorine, and bipyridine. And we identify that also using the fine R to show that there's a drop of the ruthenium chlorine intensity, because initially we have 4 chlorine here, and here we only have 2 chlorines. And so this is basically what the reaction happens with the reaction equation. The difficulty here is that we don't exactly sure about the oxidation state of ruthenium. We guess it must be reduction from 3+ to 2+. So we go to the ruthenium L edge, and this shows nicely because ruthenium 3+ is a D5 configuration. You have empty space here. So you can actually excite the chlorine 1s or the ruthenium 2p to this position. So we have an additional peak as shown here. Well, for ruthenium 2+, it's a D6 configuration. It's all full. So that basically you cannot have an electron excited here. You can only have the electron excited to here. That's why in the red curve, you don't have this feature. And the red curve is the active species, and the black curve is the initial species. So that's how we confirm that it's actually the ruthenium 2+ configuration that we're showing in the previous figure. So with that, I think I have been giving you all the 3 examples. And I want to just briefly talk about what is the future of synchrotron X-rays. In my personal understanding, I think it's faster, higher, and stronger. The faster is one of the major concerns that how you can measure spectra fast enough to capture the fundamental process. Here I plot some of the fundamental process as a function of the time scale. So you can see that the turnover is usually the millisecond or second scales. The intermediate species can be microsecond to millisecond scale. And this is our current limitation. So most of our spectroscopy have the limitation of here. But with the development of the synchrotron X-rays, it's possible to go to nanometer scales where you have the absorption, the picomecanical scales, picosecond scales, which have the desorptions, and the fundamental bond breaking dynamics, which should be within pico or femtosecond scale. So that is very important. I can briefly show you some of our examples. So for example, this is what we obtained last year in July, and we can have 2 second per spectra to show the redox of the cerium, and this is for the 3-way catalyst. So if you drive a gasoline car, you have this catalyst to purify your gasoline engines. And this is for 5 millisecond resolution, which is already 10 to the order of 3 times higher than this one. And we identify the nucleation stage of a copper, and that nucleation and reduction take place within only a few milliseconds, and the nucleation take place within a second for the formation of copper nanoparticles. And finally, this is a 250 femtoseconds, which is 10 to the minus 12 and 10 to the minus 14 seconds, which is a very fast bond breaking process of the copper oxygen bond breaking. And we can see that it's between 1 and 2 picoseconds. This is the time it requires to break a copper oxygen bond. So it's definitely possible to have a full range of the time resolved spectroscopy to identify the complete process of a single catalytic turnover. Higher space resolution is also very important because the catalyst bed in reality is always heterogeneous. Here I give you an example of the Yang Decogonwa's work here. What he is doing is the copper zeolite catalyst for the SCR reaction that happens in the diesel engine exhaust. And he identified that at a different location of the catalyst bed, the oxidation state of the copper is different. Here, it is mostly reduced copper, which is in the surface of the catalyst, while the most inside it, which is the copper 2+. So there's a heterogeneous distribution of the copper species in the bed, and of course their catalytic behaviors is completely different during the reaction. And finally, the stronger beam means that we can have higher energy resolutions, and we can see the features that is not possible before. So here I give another example. It's actually from the ESS. What I'm showing is that this is the normal dance we can get, for example, even today, we get the same spectra, which is the blue line here. But with the higher, stronger beam and higher energy resolution, then you can see actually there are a lot of features hidden inside this blue chunk here. So here is the series 3D to 4S transitions, and here's the multiple 3D 4S transitions and 3D to 6P transitions, which is not even being possible to see in the normal synchrotron X-rays. And with that, then we can identify the location of the series and of course the catalytic behavior of series. With that, I would like to summarize. So I give you 3 very basic and fundamental examples of how to use synchrotron X-rays themselves to determine the oxidation state of materials in catalysis, how the electronic structure affects their catalytic behaviors, and the local coordinations of in situ formed transient active sites. But there's more research beyond that, and there's a very huge potential of using X-rays to determine a single catalytic or fundamentals of chemistry process. So with that, I want to thank my groups, the people who did the work, our collaborators who help us to do the simulations, as well as all this range of different synchrotron resources in the UK, in Germany, Korea, and also Japan, and also the funding agencies and the companies working with us. Thank you very much.
Thank you, Ram, for your great lecture. I kind of envy you guys that you can really see how reaction works. I really look forward to the femto machine that you can see a bond breaking. Okay.
Yes, here I cheated a little bit. So here it's actually not using synchrotrons, but it's using a technique called the X-ray free electron lasers, which is there are 5 around the world, and there's a 6th one in commissioning in Shanghai. So it's the 4th generation of particle accelerators. So it's one step beyond synchrotron. So I cheated a little bit. So this should not be synchrotrons, but extra work. But yes, it's possible. And the theoretical physics people, they are even going to attosecond. So it's 10 to the minus 6, 18 second time resolution.
Great, it's coming. So I would like to take this opportunity to ask you a question. So I'm going to ask that in Chinese. 之前我有听说过，就是 X-ray 他们可以做那种低温的 frozen characterization， 就是当然有可能您做的是 heterogeneous 的，我做是均相的。然后他们说是能把那个液体在低温条件下冷冻起来，立马做一个晶体，然后做 X-ray characterization， 那种和那个 operando 的有什么区别吗？
So the question is basically about have a liquid samples, and then you during the reaction you want to capture some intermediate species, you immediately put it into the liquid nitrogen and you froze it and you measure it and you capture. So this is what we call quasi in situ spectroscopy. So basically try to mimic the operando state, but actually you don't have the operando state because the reaction is so fast. So this applies widely in synchrotron, so it's widely applied. And we also did that last year in the reaction formation of nanoparticles, so it's definitely doable.
That's great. So, because we're always looking forward to see how reaction works, especially when we have a heterogeneous reaction. It's very hard to capture the intermediates.
Yes. So, yeah.
Okay, thank you. Okay, let's see whether there are more questions coming. Okay, seems that there are no more questions for this talk, but then we're always willing to answer questions in the chat.
Yep,
all right. Yeah. Thank you, Ran. Okay, then next, we're going back to our Meet the Editors session. Let's welcome back again, Anna and Charlotte.
Hello.
Hi.
Okay. So, shall we get started with?
Yes, please.
Okay.
Yeah, and for the audience, our speakers will still also be around. If you have more questions coming later, yeah, they will be happy to answer.
Okay.
Please.
So then, before we get started with the actual discussion, I would first like to take this opportunity to thank our really excellent speakers for their presentations. I enjoyed them a lot. Yeah, and then before we get to the actual discussion, Anna and I will take 5 minutes to introduce the 2 journals that we're working for. So let me briefly share my screen. Can you see the slides now?
Yeah, perfect.
Okay, perfect. Yeah, so as Anna mentioned in the introduction, I'm the editor-in-chief of ChemCatChem, and Anna is the editor-in-chief of your JOC. And ChemCatChem, as the title of the journal might already reveal, is a journal that publishes original research and also review articles in all fields of catalysis. The journal itself was launched in 2009, so we're already 13 years old at this point, and these days we publish between 500 and 700 articles per year, and our usual acceptance rate lies somewhere between 30 and 35%. We offer a fast peer review process, and usually send out the first decision after peer review within 3 or 4 weeks. And we have also a quick production process, which usually takes 3 weeks until the final version of a manuscript is published online. And now I'll pass over to Anna to talk about your JOC.
Yeah, so the European Journal of Organic Chemistry is a little bit older than ChemCatChem. So we were founded in 1998, and this was done by merging several national European society journals with the aim to form one strong organic chemistry journal that was published in English. The journal is celebrating its 25th anniversary next year. We do publish, also as the title suggests, manuscripts, research articles, and review type articles in all areas of organic chemistry. And here it's ranging from synthetic methods over to asymmetric catalysis and total synthesis, but also bioorganic, physical organic, and supramolecular chemistry. We publish between 700 and 900 articles in 48 issues per year. So that means an issue comes out nearly every week. The acceptance rate is about 40 to 45%, and similar to ChemCatChem, we have a fast publication time. So usually within 3 to 4 weeks, you receive your first decision if the manuscript is sent out for peer review. Similar to ChemCatChem, or both journals offer the accepted article workflow. So that means once the manuscript is accepted, you can immediately publish it online, and then a few weeks later, the final version of it comes out. You can also, now that we have e-locators, cite the article immediately upon acceptance. Now I would like Charlotte to pass over to the next slide. What is Chemistry Europe? Our society publisher. Chemistry Europe is a conglomeration of 16 European chemical societies, and together we publish these 19 journals that are listed here, including UJOC, ChemCatChem, and Chemistry European Journal, which probably most of you also know. We have lots of specialized journals for a variety of different topics, and we also offer a few open access titles, such as Chemistry Open.
Our journals are run by a professional team of full-time editors that manages the entire publishing process. We manage and monitor the peer review process for our journals. We work on the post-acceptance sides of things and are involved in the production of the individual articles. We work a lot in content acquisition, so you will see that many of our journals publish several special collections per year on various topics. And our editors are also involved in social media and marketing activities and overall in journal development. And for example, we give author workshops and we run this virtual event series that you are currently enjoying. We work closely together with our society owners to publish high quality articles for our authors and readers. And in difference to other publishers in the field of chemistry, we do not have academic editors, but instead we are supported by an international editorial board, which is made up of active researchers in the respective field of the journal, and that are supporting us in scientific questions.
And thank you very much, Charlotte, for detailing what the editors do at our journals. And now I would like to introduce you to the editorial teams of UJOC and ChemCatChem. So on the left-hand side, you see the editorial team of UJOC, and on the right is the ChemCatChem team. We are highly international and also quite a diverse team, and most of the editors are located in Weinheim, or in the Weinheim office, which is in Germany, but we also have an office in China, in Shanghai, where Jyoti is located, and another office in India. So Jyoti is basically the common member between UJOC and ChemCatChem, and she's also working for Angewandte Chemie. Charlotte and I, as the editors-in-chiefs, we only work for the individual journal, but as you can see on the slide, all the other editors work for this journal plus another one, and I've listed them here, and you can see we have a wide range of expertise within the editorial teams. Next slide. As for journal promotion, we often promote our content, for example, like special issues, virtual events, and so on on our homepages and on Twitter. And for the audience in China, the chemistry journals also have a WeChat channel, which is called Wiley Chem. As you can see, we're trying to engage with our authors and audience in China and also all over the world through these channels. And we would be happy if you would follow us either on Twitter and in WeChat, on WeChat to keep up to date with our content. And if you have any questions, please also don't hesitate to reach out to us. Thank you.
Here we are. Yeah, I think our chat are kind of less behind because it's less interactive, like a live chat. So maybe I would just ask.
Yes.
Representing the audience. Yeah, I think one of the most interesting questions that I would ask is that how our editorial office works compared to ACS and the other publishers, because we have full-time editors working there. How we stand ourselves and work normally.
Yes, exactly. So our editors are full-time editors. All of us at least have a PhD in chemistry. Some of us even have a postdoc. And our team essentially covers all fields of chemistry that we publish in terms of expertise. As Judy has already said, our model is a bit different compared to the journals which are published by the ACS or by the RSC. And I would say you could compare it, for example, to the model that the Nature journals, for example, are using. So all journal matters are managed by us full-time editors rather than by academics that function also as editors as it works at the ACS or at the RSC. And I think with this, both of these models have their advantages and disadvantages. But I would say one of the advantages for our model is that we are dedicated to the job full-time, which means that, usually we'll be very quick to answer you, very quick to process your manuscripts, for example. But it also means that I think that for us, as we are not involved in the research process itself, and are kind of a bit more removed from that, I think it also helps us to keep a more open mind for things often, maybe be also less biased about certain things that are happening within academia.
Maybe if I can add, like as Charlotte said, maybe the important thing is that we do have a scientific background. So all of us, we have been in the lab before, and we did research, but then decided to take a different career path and join the publishing industry and become professional editors. And this is what we do full time. And maybe another advantage is that we oversee the whole process, maybe of a manuscript from really submission to also like the final production. So we have a very broad overview of the whole production process of the manuscripts. So it's peer review plus the post acceptance that we take in.
Yeah, thank you, Anna, Charlotte. I think also for job applications, we can also, for those students who are applying for jobs, that they can also consider it as a future career for us as editors. So then the second question, I think that's very important for those students who are eager to go deeper into academic, but then they are seeking for opportunities to work as reviewers. Then how could they approach us? And then what qualifications that they need to show? I would say there's always the opportunity to reach out to us, to the editorial office, like email us and ideally send us a CV and also maybe some
experience, like, or maybe show that they have a bit of experience in publishing and also reviewing articles, maybe during their PhD or postdoc time or in their early career stages, and we can then evaluate if the person is suitable and try them out. Ask them to sign up for Editorial Manager, which is our submission platform, and then we can send them a manuscript for review as a trial. Yeah.
Exactly. On top of that, Wiley has recently relaunched the Researcher Academy, which is an online tool that you can use to educate yourself about the peer review process. And this is something that I always recommend for advanced students that are interested in doing peer review for journals to take a look at this online course. I've posted this here in the chat now. Maybe, I don't know if Cindy can forward this to the other platform. Yeah.
Maybe another thing is there's also a section on our homepage about the whole peer review process and detailed instructions on how to evaluate a paper, write a review. They're currently being updated and should be online soon. So this is also where people can look advice on how to write a review.
Yeah, great.
Another feature that I would like to mention, maybe, for example, if your supervisor has involved you in reviewing a manuscript that he or she was asked to review, our journals offer the option to our reviewers to have a look at all the reviewer reports a manuscript received in the process. So afterwards, you can talk to your supervisor and ask them to have a look what the other reviewers said on a paper, because this is feedback that we get very often from young researchers, that it's immensely helpful to learn about how other people have reviewed the same manuscript and to see where the opinions maybe differed or where they were of the same opinion. And it really helps to think about what you can maybe do better for the next paper that you're reviewing.
Yeah, I think that's great. And Professor Shi, do you have any good other ideas about how students could be involved in the peer reviewing process? Maybe we can talk that in Chinese. Okay.
Okay, thank you.
Yeah.
I would like to speak in Chinese. 作为审稿人，我觉得主要呢是一个是对这个稿件的质量，就是进行一个控制。看它的创新性是不是达到了一个期刊的一个要求，这是一个，就是帮期刊来把关，筛选出符合期刊要求的这样一个文章。第二个呢，我觉得是给作者提供一些建设性的意见。就是有些可能是作者意识不到的，那么通过几位审稿人的建议呢，我觉得这是对作者也是一种负责，所以我觉得作者看到审稿意见，有时候他应该就是不要是觉得是审稿人给他挑毛病，而是说是审稿人是为了让这个稿件更加完善。所以我觉得，有些方面呢，如果自己即使补实验达不到的，可以跟审稿人进行一个沟通。我觉得这样呢，双方可能都能理解。所以我觉得审稿呢，就是要坚持这个期刊的一些标准，然后给作者提出一些建设性的意见，包括它的内容，包括它的形式，等等这些方面。时间关系呢，我就只大概介绍这一点。
是的，谢谢石老师说的很好。就是其实审稿人大部分时候都是为了让那个稿子变得更完善，所以大家审稿的时候也注意一下，就是不要就是可以挑剔，但是不要过分挑剔。当然也要根据不同期刊的标准来做一个评审依据，因为不同期刊的要求是不一样的。
对，是的。
行，谢谢石老师。Ryan, do you have anything else to add into this point?
Yes, we have a recent manuscript unfortunately rejected by one of the very good journals, and then we discovered some mechanism that is not discovered before, and then all the reviewers says that no, we need to study all the mechanisms. This is the correct one. This is the holy grail. You're wrong. We are right. And this is what I regarded as not very useful reviewers.
Yeah. So be constructive, I would say. Okay. Yeah. Great. Thank you. Yeah. Sorry.
Can I just add one thing? What I wanted to mention is that if you are a supervisor that is involving, let's say, very advanced PhD students or postdocs in the peer review process, we always appreciate it when you submit the report that you let us know in the field that says comment to the editor that someone else has helped you with preparing this report. That's very helpful information for us. And it's always appreciated if you share this with us.
Or if you don't have time, but a very capable person in your group, like an advanced postdoc, you can also recommend, this person, give us the email address, and then we can register the person in our system and approach him or her directly. So that's also
which is also a very good option, because with this, this person will be able to get certification that they did actually write the review through Publons, which we offer. And this, I think, is often very interesting for younger researchers when they are applying for academic positions, for example, because Publons really shows a track record of how many papers you have peer reviewed in the past.
And if you do a good job, the chances are high that we have you again. Yeah.
Sure. Okay.
We'll keep that in mind.
Yeah. Then we have another question that might be more specifically for non-English speaking authors. So for those there who are non-speaking, but they need to prepare the manuscript in English, and then how the editorial office will treat those manuscripts that are not perfectly in English, but scientifically great.
Usually we do not treat manuscripts differently when it comes to the level of English, as long as we're able to understand the paper.
Yeah.
So let's say if the level of English is quite low, then unfortunately the chances that it will be sent out for peer review are not very high. The reason is that if it's difficult to really understand all the details of the paper, it will be very difficult for a reviewer to fully assess the paper and the science there. What we do in such cases is we put you in touch, or we give you information about copy editing services that can help you to get a manuscript in a better shape, and that will definitely increase your chances of your manuscript to be sent out for peer review.
And a general recommendation for non-natives is just to keep the language simple. Like, don't try to use overcomplicated words or long sentences. Just keep the language simple, and that's fine. There's no need to, use very fancy words or something. Like, as long as we can understand it, the English is correct and the science is good, then that's all.
And of course, we always recommend to have your manuscripts read by several co-workers before you submit it, because this will definitely help you to catch some mistakes and to overall polish the manuscript before it's submitted to a journal.
Yeah, and maybe here also someone that is not directly related to your topic. Maybe ask someone that knows the area a bit, but is not an expert, because then they can help you also in terms of, is it understandable? Do the right things come across or get across? So this is helpful.
Yeah, Professor Shi, then I know that your English is great, but then how's your experience with those? So, for example, submitting an article as a non-English speaking author, then how the journals normally feedback to you?
Okay. In my experience, I always, before my submission, manuscript to some journal. In some cases, I will ask some agencies, some agency to help me to polish the language of this manuscript, because I think maybe I read the manuscript, I think it's fluent, but in some cases, some reviewers ask me to polish the language. That I will send the manuscript to some professional agencies. I think it works very well. So normally I will prepare my manuscript in this way.
是的，谢谢石老师，这也是一个很好的方式。现在咱们国内也有很多的，就是那种打辅助的机构来帮助我们来提升文章的质量。
是的，
行，那最后还有一个就是给所有的听众的，就是我们现在 Wiley Office 在中国有2个分部，一个在上海，一个在北京。然后我们也有很多的编辑同事，非常乐意的和大家交流关于写作呀、投稿的方方面面的事情。所以如果大家对这方面感兴趣的话，我们可以给大家提供不同的讲座。然后大家可以刚刚那个 slide 我再重新 share 一下，大家可以 follow 那个 Wiley Chem 的公众号，然后如果有什么事情的话，可以在 Wiley Chem 公众号上联系我们。Sorry， 这一个 ，OK， 这一个。如果大家有什么事情可以联系我们，然后关于投稿，如果想要进行一个讲座的话，也可以联系我，我们同事会组织来给大家分享经验呀，然后给予一些专业的指导。Okay, so then I don't have any more questions here. I think if the audience would be willing to share more, and we can be in touch anytime via email or our WeChat and Twitter. So I think due to time limit, we might have to close the session for now. Yeah. Thank you all for being here today. Yeah. Miss Charlotte.
No, I just wanted to say thank you to everyone involved. Yeah.
Yeah, also from my side, thank you to all the speakers. It was really fantastic and interesting to listen to your talks, and thank you for the audience for watching and everyone who helped organize it. Yeah.
Okay, thank you. Thank you, Anne. Thank you, Carla. Thank you, Judy. Thank you, everyone.
Thank you.
Thank you, everyone. Yeah.
Have a good evening.
Everyone.
Bye.
Have a good
Take
day.
care.
Bye.
Bye.